What's up, guys? We're going to go through a concept map for Unit 6, Simple Harmonic Motion. So let's go ahead and get started. So the first thing I'm going to do is, this is a concept map where we're going to walk through the basic key points of Simple Harmonic Motion. There may be more to add on later, but this is what I see so far. So we got Simple Harmonic Motion at the top, like we do for most of our concept maps. First thing I'm going to talk about is it's going to be Hooke's Law. So, Hooke's Law, which is one of those big key laws in AP Physics that they like to talk about frequently, and that is the force on a spring is proportional to its spring constant times its stretch distance. Now, you're going to notice that on your reference sheet, it's got these absolute value signs around it. And all that is because you have to denote what direction that force is going, and we'll get more here there soon. So what we got here is if I have a spring that's holding a mass downwards versus a spring that is holding a spring horizontally, what is the difference here? And for this one, it's the force that's on the spring is going to be equal to weight. And that's just basically because we've got weight going downwards, and then we have our spring force going upwards. Such as things you have to denote the direction. And then if it's horizontal, either somebody holding it or a friction full surface, what we're going to say then is that we're going to call to the right is going to be a force applied, while to the left is going to be the force of the spring. And so what we say here is that the force of the spring is equal to force applied, or if it's on like a friction surface, you could say force of friction, if everything is standing nice and still. The unit of K, that's your spring constant, and that's going to be in units of newtons per meter. X is going to be your stretch distance, and that's also going to be in meters. In this unit, which you find very frequently, is that you're in centimeters and you have to convert over. So make sure anytime you see centimeters, go ahead and just convert it on over to meters, and then you're good to go there. The one thing that I do see people get stumped a lot on is that this stretch distance is your stretch distance, not your final distance. So if we have a spring that unstretched, it is 10 centimeters, but then I pull it with a force, and now it goes to 12 centimeters. A lot of people get tripped up and just put 12 in here as their final distance, and so no, your change in displacement here, or your total stretch distance, is actually just 2 centimeters. All right. So that's going to be it for Hooke's Law. What about what you find typically with what is simple harmonic motion? So all simple harmonic motion has to follow some basic tenets. One, there has to be a restoring force proportional to the displacement from equilibrium. And what do I mean by that? Is that the force that's causing your action to go back and forth, kind of like a pendulum or a spring set in motion, is that the restoring force, what's causing it to go back to equilibrium, is proportional displacement. And then the second thing is that your equilibrium is your midpoint. So let's go through a couple examples of what that looks like. The first one would be a pendulum. So let's do a pendulum that is oscillating back and forth. So I've got a pendulum here oscillating back and forth. Does this fit the criteria? Well, yes. The restoring force here is going to be, let me use a different color for this. The restoring force here is going to be weight. That would be parallel. So weight parallel is what's actually causing it to go backwards towards equilibrium. The further you pull that away, the higher and higher value weight parallel gets closer to acceleration due to gravity. So when you look at a pendulum, acceleration is at its highest at the ends. And so the force on it, or you could even then say the F net, so if we were to look at this and how this is proportional to F net, the restoring force on it is definitely proportional to how far you pull back. If we pull back a pendulum just a little bit, there's not much restoring force going there. So, second thing is the midpoint through the equilibrium. And absolutely, we find that right down the middle, our equilibrium point is at our midpoint. Alright, so is the force proportional to displacement? Yes. From equilibrium? Yes. What about a spring system? So I'm going to draw just a couple boxes. If I've got a spring system in motion, we'll call this the bottom of the motion, this the midpoint, and then this the highest point of that oscillation. Does this still fit the criteria? Well, the further you pull that spring down, the further restoring force upward is going to be. And the equilibrium is at the midpoint. So there we go. So this right here shows us that whether you pull a spring or you push a spring, the restoring force is always going to be going towards equilibrium. So if we put a pendulum in motion, that's clearly going to be simple harmonic. Or if you put a spring system in motion, it's still going to be a simple harmonic motion. So down here, what I'm just going to put on also is that F net is often just going to be equal to weight parallel here. And if you need help with how breaking those two components, I would just suggest drawing a free body diagram and then go from there. So F net equals what? Weight parallel. And so then from there, we're also going to say that is also proportional to the acceleration of the system. Over here, F net is going to be equal to your restoring force or your spring force often if it's at the bottom, so right here, and then often F net at the top is going to be so this will be spring force minus weight, and this will be spring force plus weight. That's because if we were to draw free body diagrams, weight's still going to be going downwards. So we got spring force and going up when it's at the bottom, and then going down when it's at the top. And so F net there is going to look just a little bit differently. But you tend to still always get the acceleration is going to be at a maximum at the top at either extremes. So in the same way acceleration is at a maximum at either extremes on the pendulum, it's going to be the same thing with a spring system in motion. Alright, let's move this on down just a little bit. If I can find my mouse, where'd it go? There it is. So I'm going to move this down just a little bit. Okay, and we're going to... I don't know where that box came from. We're just going to run with it. We're going to talk a little bit about what can you do with a spring system and what can you do with a pendulum system. So on your reference sheet, there are two formulas for you to have. So you can either go in the way of a pendulum, or you can go in the direction of a spring system. So depending on what we're looking at, changes what we do. Move this down just a hair. There we go. So the pendulum system is, period of a pendulum system is 2 pi square root L over G. Let me erase that. Maybe just look a little bit nicer. Now we'll try this again. Period of pendulum. Maybe I have to go a little bit bigger. And then period of a spring is 2 pi square root m over k. So there's a couple things I want to denote here. You see 2 is constant, you see pi is constant. This has to do in reference of the unit circle. Excuse me. But let's look at a couple of relationships here, because this is where they like to get tricky with it. If we were to break down this relationship, what would be the relationship between mass of this pendulum and the period of this pendulum? Length. I got it backwards on. Whoop. Let's do length first. Mass is later. Period of this pendulum versus length. Well, that, if I were to knock this down that would be the period of a pendulum is proportional to the square root of the length. So what you can do actually for these kind of things is you can knock off all the variables that you don't need. And so a lot of people don't quite see what this gets you, and so it's not very easy to see that this relationship here is an inverse exponential relation. No, it is a exponentially decreasing square root relationship. Sorry, that was tough. But how do you linearize this? That's the big part. That's the part that's easy for us to unpack. And so what we say is the period of a spring with length squared. I'm sorry, not. Oh. I got it backwards on my period squared over length. Looking down at my reference sheet, and I got it backwards. So, how do we get here? Well, I'm going to pull this down here just a little bit, and if I square both sides, that gets me period squared is proportional to length. Now, if we graph period squared and length, this linearizes my data. Now, linearization of data is a real big skill point in AP Physics, and so learning how to linearize your data. So what we do is I just treat this whole thing as my y, treat this whole thing as my x, and you get a nice linearization of data. What about if we were to change gravity? So that would be, let's do this in green. The period of a pendulum is proportional to the inverse square root of gravity. So what would this look like? And this is a pretty hard one just to kind of throw off in your head, but it's just going to be a real steep inverse relationship. Now, how would you linearize this? And what I would recommend students do is they would then graph this again and do period of a pendulum squared over gravity, and you get a little more linearization of data. It won't be perfect, but it will definitely be a whole lot more linear. All right, let's go hop over to springs. So when you look at the period of a spring versus mass, and the period of a spring versus spring constant, that it follows the same relationships as it does for pendulum, that this is going to be proportional to square root of m. So it's going to look something like this. And the way to linearize that is to square your data. So square both sides. What you get is period squared is proportional to mass. Same thing for k, is that it's going to follow a very steep inverse. So what we do is we're able to linearize our data just a little bit, not quite 100% linearize, but definitely get on the right track by squaring that. Well, let's talk about some variables that aren't here. Where is mass in a pendulum? So where is mass at? And this does not show up in your formula at all. So this is one huge big part that they like to trip people up when it comes to pendulums. If I change the mass of a pendulum, how does it change the period? It doesn't. So mass has no relation to the period of a pendulum. Mass does have a relationship to the restoring force, but as you increase mass, your restoring force also increases, but your acceleration doesn't change. Alrighty, and what about how far back I pull that pendulum? Well, we would call that our amplitude or angle theta, and theta also has no relation. So you could pull a pendulum back 10 centimeters, you can pull back 20 or 30, let go, and that period will remain the same. Let's hop back over to springs. What does not show up? Well, when you look at a spring, what do we know so far? We know stretch distance. How is that related to the period of spring? It's not. And what else do we know? Gravity. Does gravity have any relationship with the period of a spring? It sure does not. Does it have a role to play when you're looking at restoring forces? Yes, but it does not change the period one bit. Alright, moving on down. Oh, it won't let me move on down anymore. Let's go to a new page. So, let's look at when we're talking about energies. So if I'm going to continue down here with the period of a pendulum, so we're talking about pendulum still. Let's talk about the energies in a pendulum. Well, what we know about a pendulum is while it swings, drawing a pendulum real quickly here, is that the potential energy, that the total energy is conserved. So total energy conserved, or total mechanical energy. From there, we know that the potential energy at the top is going to be at the highest, and the kinetic energy at the bottom is going to be at the highest when you're looking at the frame of reference of this height. Okay, if we were to go to the ground or different, your potential energies would change. But here's what we could say with this. If we look at, I'm going to draw this just a hair bit better. If we look at this as our height, we can then say that the potential energy at the top equals the kinetic energy at the bottom. The gravitational potential energy specifically. So here you can unpack this a little bit and then say 1/2 mv squared at the bottom equals mgh at the top, or the height from the bottom. And so what you notice here is mass cancels out. And so we find again that mass has no relationship in a pendulum. Alright, let's talk about a couple things. So what do we know about if the kinetic energy is the highest at the bottom? We also know that the velocity at the bottom is the highest. So let's do this right here. Let's do this right here. Velocity is at the highest at the bottom. Acceleration is at the highest at the top. And what can we say about velocity at the ends? So let's do this. Let's erase that just a little bit. We also know velocity at the ends is at its lowest, so it's 0. And yeah, I think that's pretty much it we're going to say about that. We can also say acceleration down here is going to be 0. So when it passes the midpoint, your velocities are actually going to be changing directions. Your acceleration is going to be changing directions. And so because of that, it has to cross 0 at some point. Alright, now let's move on from that ugliness and let's look at springs some more. So if I were to draw a spring system again, this time let's make it horizontal. And let's draw our equilibrium from right here. Okay. What do we know about the potential energies and the kinetic energies? Well, and similar to at equilibrium, we know our kinetic energy is going to be 100% of your mechanical energy. It's going to be all of your energy from potential is going to go to kinetic. But we just say this is at equilibrium and not necessarily at the bottom. At your extremes, we know that all of your energy turns into spring energy. Now this is U sub S, not U sub G. So we oscillate back and forth. From there, we're able to unpack just a little bit and saying acceleration is at your highest at the ends. And that means acceleration for a brief moment of time is going to be 0 at equilibrium. Velocities are going to be 0 at your ends because they're changing directions. They're coming back. And your velocity is at a max when it comes to coming across that equilibrium. So let's unpack that a little bit. What can we say about here? So here we did the math for a pendulum. Let's do this now for a spring system. So K, probably my faces are right over here, so I'm going to do this over here. So K at equilibrium is going to equal spring potential energy. Now, spring potential energy is something we haven't unpacked yet, and that is 1/2 kx squared. So what we get here is kinetic energy is 1/2 mv squared. Spring energy is 1/2 kx squared. And so we do find here mass does have a role to play. So I earlier talked about there's no relationship in mass on the period of a pendulum. There is a relationship with mass on the period of a spring system, and we see that pop up right here. Alrighty. Well, ladies and gentlemen, I believe we're going to call that it for this video. And good luck. And if you have any questions, let me know.